Hello, chemistry students. In this video, you will learn Dalton's atomic theory. You will learn about electrons, protons, and neutrons. You will learn Thompson's model of an atom, Rutherford's experiment for the discovery of nucleus, and the structure of the atom. Let's start with Dalton's atomic theory. The credit for the beginning of the model of atomic theory is given to John Dalton. John Dalton's atomic theory is the true reflection of scientific method. It was formulated as an explanation for a number of laws about how matter behaves in a chemical reaction. The first law is law of conservation of matter, and the second law that we will see is law of constant composition. Let's look at these laws one by one. The first law that led to Dalton's postulate his atomic theory is law of conservation of matter. According to this law, when a chemical reaction takes place, matter is neither created nor destroyed. In reality, conservation of matter in a chemical reaction is not easy to determine, and many reactions seems to either create or destroy matter. We can see it from the following two examples. In the first example, I have a glass of water and two tablets of Alka-Seltzer. Mass of these two reactants is 281.97 gram. When we add these two tablets to the water, looks like the mass is lost and matter seems to be not conserved. But in actual, the mass that seems to be lost is the mass of the carbon dioxide that is produced from the reaction of Alka-Seltzer and water, and this carbon dioxide is escaped from the reaction mixture. So matter is not lost during the reaction, but is conserved. In the second example, I have an iron nail of 2.25 gram, and in the process of getting rust, it seems like the matter is not conserved and gained by 0.02 gram. But in actual, this gain in the mass is actually the mass of oxygen and water vapor from environment. So matter is not created in this reaction, but it is conserved. To confirm the law of conservation of matter, number of experiments were carried out in sealed vessels where no matter can enter or leave the vessel. And under these conditions, it was confirmed that matter is always conserved. The second law that led to Dalton's postulate his atomic theory is the law of constant composition. According to this law, multiple samples of any pure chemical compound always contain the same percent by mass of each element making up the compound. To see examples that support law of constant composition, we have to learn how to calculate percent by mass of an element in a compound. Steps on this slide will help you to calculate the percent by mass of an element in a compound. Step number one is determine the mass of each element in a compound from the information given. Step number two is determine the total mass of the compound. Sometimes the total mass of the compound is given as is in a problem, and sometimes you have to add the mass of each individual element to find the total mass of the compound. Step number three is divide the mass of each element by total mass of the compound and multiply it by 100% to determine the percent composition of each element. Step number four is to check your answer, and you can do it by adding all the percent composition of all the elements, and you will get something close to 100%. The example is that if a 50.0 gram sample of pure water is decomposed into its component elements, you will obtain 5.6 gram of hydrogen gas and 44.4 grams of oxygen gas. You have to calculate percent by mass of these elements. Okay, so let's see the information given. So we have the mass of the sample, okay, which is the mass of the compound. We have the mass of hydrogen gas and mass of oxygen gas. Here is our formula. We can use this formula one time for hydrogen and then for oxygen. We have two elements in water, hydrogen and oxygen. So let's solve the percent composition of both. So percent composition of hydrogen will be, we need mass of hydrogen element, which is 5.6 gram. We need mass of the compound, which is 50.0 gram. Multiply it by 100%. On my calculator, I have 11.2%. I will look for my sig figs. Here I have 2 sig figs. Here I have 3 sig figs. For 100, it is the part of the formula, so it is exact number and I will not count any sig fig in it. I will round my answer to 2 sig fig and it will be 11%. For percent composition of oxygen, I need mass of oxygen, which is 44.4 gram. Mass of compound is 50.0 gram. Multiply by 100%. And I have 88.8%. My sig figs, here I have 3 sig figs, 3 sig figs, and 3 sig fig in my answer. Okay, so this will be my answer, and to check my answer, what I can do is I can simply add 88.8 and 11%, and you can see that your answer will come out very close to 100. I have 99.8% because I'm using this rounded one. If I use unrounded, it will come out like exactly 100%. So law of constant composition is multiple samples of pure compounds always contain same percent by mass of each element in it. So no matter we have the water sample from Earth, from Mars, from New York, from any part of the universe, it will always give you hydrogen as 11% and oxygen as 88.8%. So the percent composition for hydrogen and oxygen will always come out the number that we have on the slide. And if it is some other percent composition, then it will not be water or H2O. Let's do another example. For this example, how about you guys pause this video, solve the problem at your own, and then play the video to check your answer. In this example, we have 25.00 gram of sample PCl3. We have 5.6 gram of phosphorus, and you can see that the mass of chlorine is not given. We can use our weighing by difference technique, and where you have the mass of total given and mass of one component given. If you subtract these two, you can find the mass of the other component. So let's find the mass of chlorine first. Mass of total is 25 and mass of one of the component is 5.64 gram, and you have 19.36 gram chlorine. For our sig fig or decimal place, you can see here you have 2 decimal places. Here you have 2 decimal places, and in your answer as well you have 2 decimal places, so we don't have to do any rounding. Now we have mass of chlorine, we have mass of phosphorus, and the total mass of sample is given here as well. We can use all these numbers to find the percent composition of each element. So let's start with chlorine. So percent composition of chlorine will be, we need mass of chlorine, which is 19.36 gram. Total mass of the sample is 25.00 gram. And we have 77.44%. In terms of sig fig, you can see that under this bracket that we have from here, we have 4 sig figs. Here as well, we have 4 sig fig, and in your answer, you have 4 sig figs, so you do not have to do any further rounding here. For percent composition of phosphorus, we will start with the mass of phosphorus, which is 5.64 gram, divided by mass of total, which is 25. multiply 100%, and I have 22.56% on my calculator. Let's look at our sig figs. So here we have 3 sig figs, 4 sig figs. So we have to round our answer up to 3 sig figs. So the number after the last digit to be keep is greater than 5. So we are going to round up, and this will be the answer for percent composition of phosphorus. So sample of a PCl3, no matter where we take it from, will always have chlorine as 77% and phosphorus 22%. Based on law of conservation of matter and law of constant composition, Dalton formulated his atomic theory, which can be summarized in 5 short statements. Number 1 is all matter is made up of atoms. Atoms are small, invisible, indestructible, fundamental particles. Second statement is atoms can neither be created nor destroyed. They remain unchanged all the time. Third point is atoms of a particular elements are alike in size, in mass, in chemical, physical properties. Fourth point is atoms of different elements are different from one another. They have different sizes, different masses, and different properties or behaviors. Fifth point is a chemical reaction involves either the union or the separation of individual atoms. Nearly 200 years after Dalton proposed his atomic model, we now know that none of his 5 statements of his theory is entirely true. Atoms are not the most fundamental particles. They are composed of even smaller particles. We call them electrons, protons, and neutrons. Atoms can be created and destroyed, but a nuclear process is required to do so. Let's keep moving to see how the model of atomic structure was developed. In 1897, Thomson discovered the first subatomic particle, the electron. Here I have some properties of electrons that you guys need to know. All atoms contains electrons. These electrons were very small, lightweight particles having 1 by 1836 the mass of the hydrogen atom. Mass of the hydrogen atom is 1, and 1 by 1836 the mass of the hydrogen atom. You can divide and see how light the weight of the electron is. The electron has a negative electrical charge, and the value of 1 electron is -1. If you have 5 electrons in an atom, the charge of 5 electrons will be -5. The first atomic model was proposed by J.J. Thomson shortly after the discovery of electron. At that time, he knew 2 basic facts about atoms. One is that atoms contain small, negatively charged particles called electrons. And the second is that the atoms of an element behave as if they have no electrical charge at all, and they are all electrically neutral. At that time, Thomson reasoned that there must be something inside the atom that carries positive charge to neutralize the electron. Thomson's model of atom consists of a cloud of positively charged electricity in which the negatively charged electrons are embedded. And this model is known as plum pudding model because it reminds many scientists of the classic English pudding. You can see that these negatively charged electrons are embedded like plum in the pudding. In 1907, Thomson and E. Goldstein found another subatomic particle that was present in all atoms, and that particle is called as proton. Here I have some properties of protons that you need to know. All atoms contain protons. This particle was much heavier than electron with a mass of almost equal to that of a hydrogen atom. Mass of a hydrogen atom is 1 and the mass of the proton is almost equal to the mass of the hydrogen. The charge on the proton is positive. Its magnitude is equal to electron with opposite sign. The charge of one proton is positive 1, and if an element have 5 protons, the charge will be positive 5. For 10 protons, it will be positive 10. 25 years later, Chadwick demonstrated the existence of a third subatomic particle, the neutron. The points that we need to know about the neutrons are most of the atoms contain neutron. You can see that this is different than the points that we learned for the electron and proton. Electrons and protons are in all atoms. But for neutron, you can see it is most of the atoms contained neutron. It means that there are some atoms that do not have neutrons in it. And you will see that in this course. It had about the same mass as the proton. Remember, the mass of the proton is about the mass of the hydrogen, which is 1, and the mass of the neutron is same as the mass of the proton, so that is also equal to the mass of the hydrogen. So that is also close to the mass of the hydrogen. A very important thing about neutron is that neutron does not have any electrical charge. They are neutral with zero charge on it. Our next topic is Rutherford's alpha particle experiment. This experiment led to the discovery of nucleus. Before we see the experiment, let's look at the properties of alpha particles. Alpha particles are small chunks of fast-moving, positively charged matter that are spontaneously and randomly given off by many naturally occurring radioactive elements like radium, polonium, radon. Alpha particles consist of 2 protons and 2 neutrons and giving it a charge of positive 2. Remember, the charge of 1 proton is positive 1 and 2 protons will be positive 2. For neutrons, there is no charge. So if alpha particles only consist protons and neutrons, then the charge of the alpha particle will be positive 2. Another thing that you need to remember about the property of the alpha particle is that they are small in size, fast moving, and positively charged. On this slide, I have the setup for the Rutherford's alpha particle experiment. In this experiment, the radioactive source is inside this lead box with a little opening to emit the alpha particles. Rutherford thought of alpha particles as positively charged bullets that could be fired at various angles. And the targets that he chose were thin foils of pure metals. And in this slide, you can see he has a sheet of pure gold. Rutherford decided to fire alpha particles at the gold foil to see what happened. And as he cannot see either alpha particles or the individual atoms of gold in the foil target, what he did is he positioned the screens coated with zinc sulfide at different angles. These zinc sulfide screens will glow when the alpha particles will strike on them and will help him determine the path of the alpha particles. Rutherford's expectation based on the plum pudding model was that all alpha particles will cruise through the gold atoms pretty much undisturbed because most of the space inside the atom is empty. But what he observed that most of the alpha particles did went straight through the gold foil because he saw a big glow in the middle. Some alpha particles deflected at the wide angles, and some of the alpha particles bounced back towards the source. Conclusion of Rutherford's alpha particle experiment. Based on the number of alpha particles deflected and their angles of deflection, Rutherford was able to calculate the relative size of electron space in the nucleus, and he concluded that there must be something small and massive inside each gold atom, and he called it the atom's nucleus. And the other point that he concluded is that atom must be mostly empty space, and the empty space is occupied by much less massive electrons that are present in the atom. Let's look at the background of why these alpha particles deflected and bounced back towards the source. Alpha particles are positively charged small particles, and if we have something inside the atom that is positive, so like charges, positively charged alpha particle and positively charged nucleus will repel each other, and due to that repulsion, the alpha particle will bounce back depending on how close it is towards the source or deflect with a wide angle. And the alpha particles that are passing through the empty space where we only have electrons will cruise through the film without any deflection. And as most of the space inside the atom is empty, that's why most of the alpha particles passed through this gold foil without any deflection, but some were deflected with a wide angle when they hit the nucleus. Let's have a summary of structure of atom. We have protons and neutrons. Protons and neutrons are located in the nucleus of the atom. The nucleus is small compared to overall size of the atom, and the majority of the space of an atom is the space in which electrons move around. Here is the atomic structure. We have a very teeny tiny nucleus, and this nucleus is actually consists of protons and neutrons. Charge on the proton for one proton is +1. Neutrons are neutral, there is no charge. We have electrons moving around the nucleus, and the charge of one electron is -1. For their masses, the mass of proton is close to the mass of hydrogen, and it is 1.007 AMU. Proton is found in all nuclei. AMU is the unit, atomic mass unit, and we use this unit to represent the masses of electrons, protons, neutrons, and atoms. Mass of the neutron is about same as the mass of the proton, and it is 1.009 AMU. It is found in almost all nuclei except most hydrogen nuclei. For electron, its mass is 1 by 1836 the mass of the proton, and it is found outside the nucleus.